suppose I have to have two nodes. The smallest I could do is, how much of a wave is that? How much of a wave is that I drew up there? That's half a wavelength, right? This is 1/2 lambda. Does that make sense to everybody? Can you see that's half a wavelength? Because the next one below it, the wave goes up and comes back down, so that makes this 1 wavelength, right? A whole wavelength there, right? Looking at the open on both ends, how much of a wave is that? That's not a whole one. It's half. It's half. Yeah, see, I've got, how much is this little segment right here? Well, that's half of whatever the closed one was, right? So this little segment is 1/4, right? And there's another 1/4. So this is going to be,
Wait, why is the 1/4 instead of half?
half a wavelength. A half looks like this over here, right? Half looks like this over here. So imagine, if you will, cutting this guy in half right there. Imagine cutting him in half, and then grabbing this chunk on your right, picking him up, and putting him over on the other side, where the two nodes touch and become one. You see that? Okay? Meaning that's a half over there also. And what's this? Well, I got a half here in the center, right? This part's a half, and that part, what are those other two parts on the end? 1/4, meaning this adds up to being 1. So this is going to be lambda, right? 1 wavelength is able to form, and then we're able to go up from there, right? We're able to go up from there. Open on one end, though, is odd. We said this was how much of a wavelength? 1/4? How about this? How much is that? 3/4. Okay? So what you have just told me is the equation for standing waves. The length of the string or the pipe, whatever you're dealing with, is equal to n lambda over 2. The length of the pipe that you're dealing with is equal to n being the harmonic number. First harmonic, fundamental, n equals 1, second harmonic, third, fourth, whatever. N lambda over 2. Length of the pipe, length of the string, length of whatever, n lambda over 2. We're open on one end. If you're open on one end, you can only have offs. You can only have the offs. Now, combine that equation with the standard wave equation. Velocity of a wave equals what? Yeah. Wavelength times frequency. Combine those two and you're able to solve whatever problem you want. Solve whatever problem you want. Okay. Yes?
We know the third, just a third harmonic.
Sure. Open on both ends, third harmonic. Okay, so I've got to have, now just to fit my drawing in, I'm going to make my pipe a little bit longer. Understand, the pipe doesn't have to get longer to get it in there. The same pipe forms all the different harmonics, okay? But just for drawing's sake, I'm going to make my pipe a little bit longer. It's got to be open on both ends, right? And instead of having 2 nodes, I'm going to have how many? 3, right? So it's going to hold on here. What did I mess up? Trace some ends of the pipe, and there you go. There'd be the third harmonic. That has 1.5 lambda in it. That has 1.5 lambda in it, or 3/2 lambda. Okay. This equation should make sense to you. I mean, come back and look at. Let's use the open on both ends idea, right? L equals length of this pipe equals, right, n lambda over 2, where n is 1, right? Which is what we said, 1/2 lambda. This one down here, this is the second harmonic. Length of the pipe, that's how long the pipe is, has one wavelength in it, which n being 2 lambda over 2. The length of the pipe is how long the wavelength is. And then down here, L equals n, this being the third one, lambda over 2, 3/2, which that is. Read. Yeah, we're talking about a natural pipe. So let's do a little demo with that. Over 4. Yeah, open on one end, good, is going to be, this is 3/4 lambda. So the equation over here is going to be L equals n lambda over 4. N lambda over 4. Okay? So let's do a little demo here. Let's see if it works. Yeah. Now, I'm not talking about the electronic organ, right, that simulates it. I'm talking about the real old organ. Does the church around here have one of the big, booming, huge organs? Okay, cool. It's especially really cool whenever if you get the chance to go to one of the famous old churches, famous old Catholic. It's not called a church at that time. It's called a cathedral. Thank you. Right. If you get a chance to go there, like one in England or New York City, because those organs. Holy nice. Sorry.
What about the Cleveland?
Oh yeah. It's all King's Church. Anyway, I completely mess this sort of stuff up, so I apologize for insults that I have to say. If you get a chance to go in there, in any of those, I mean, just massive pipes. It's so much fun. Now, whenever they're dealing with really, really low notes, obviously they're going to be bigger pipes, right? The lower the notes you want to hit, the longer the pipe has to actually be. But they also use a trick, and here's what I want us to figure out. I've got a pipe. Well, let's turn it more vertical, because that's kind of how organs work, right? I've got a pipe, right, that is, I don't know, let's say 4.9 meters long. 4.9 meters long. And I want you to run a comparison for me. I want you to compare this pipe, open on both ends, 4.9 meters long. I want you to compare this pipe if it was open on both ends or closed on both ends. And I want you to find for me the fundamental frequency that those pipes would play. The only difference between them, one is closed, one is open. So find for me the fundamental frequency that those pipes would play. The two equations we're actually dealing with are standing wave equation, right? If it's open on only one end, like that first pipe, it's going to be n lambda divided by 4, or open on both ends, that'd be n lambda divided by 2, right? And the speed of a wave equation, right? So I'm looking for frequency, right? I'm looking for frequency, just thinking through this logically. I could solve for frequency if I knew wavelength, right? Because I know the velocity of sound. That's what an organ pipe puts out, right? I know the velocity of sound. So if I knew wavelength, I could solve for frequency. How can I find wavelength? Well, I can use the equation L equals n lambda over 4, right? So thinking through this backwards, those are the two equations that I want to use. Now let's actually try to solve this. For open on both ends, I got, for open on only one end, 4.9 equals 1 L divided by 4, right? So what is the length? What is the wavelength for open on one end, please?
2.6
19.6 meters, about 19.6 meters. Plug that in. 340 equals 19.6 F. F with one end open. What's the frequency? 17.3 hertz. 17.3 hertz. How many sig figs did I give you in this problem? Two. So what does this need to become? 17 hertz. Okay. Great. So about 17 hertz. All right. Now for the other one, I'm going to use the exact same process, right? Exact same process. Length equals n lambda. Now, what's the equation for open on both ends? Over 2. Closed on both ends or open on both ends? It's n, or L equals n lambda divided by 2. Okay, so this is over 2. 4.9 equals 1 times lambda divided by 2. What does lambda come out to be? I'm sorry? 9.8. Good. Meters. So plugging into V equals lambda F. What is frequency of both sides? Open. With sig figs 35. So whenever you're trying to design pipes, hit really, really low notes for an organ, what type of pipe do you want? Well, I want them to be closed on one end, right? Closed on one end. Because if they're open on both ends, the same length pipe actually plays a higher note. Next time you go to church and you look at a pipe organ, check that out. The bigger ones will be closed on the bottom. The smaller ones will be open. The advantage to being closed on one end is you actually get lower notes. What's the disadvantage to being closed on one end? Well, the sound's going to come out and, disperse. There's only certain harmonics you can play. There are only certain notes that pipe can hit, right? Because of the harmonics. In fact, it ends up skipping certain ones. Does that make sense? It's up skipping certain ones. Where the open on both ends can play the first, second, third, fourth, fifth harmonic, right? The closed on one end, yeah, that's great. You can hit really, really low notes, but you can only play the first, the third, the fifth harmonic, so on and so on, the odds. You can't play the even harmonics. You have to skip notes. Okay? So whenever you're trying to hit the really low guys, there's an advantage for closed on one end, but in general, for pipe organs, you're going to see all the pipes open on both sides. That way, each pipe has a greater range. Make sense? Cool. Yeah, well, if you have the room to have just tons and tons and tons of pipes, great. But you don't really have room. Anybody actually play organ? Okay. The organ actually has a massive range. The traditional pipe organ has a massive range. Okay. Way more than each pipe playing one note. Way more than with the average organ, each pipe playing one note. Each pipe can play multiple notes depending on which harmonic it is that you're dealing with.